Hello, my name is Steve Sanders. I've done astronomy for the last 11 years of my life, and the other day my friend said, well, why don't you do a blog on it, or talk about it, or do something kind of fun? And I said, why not? So I'm going to actually start a blog. This is the first one. I have no idea how it's going to go. It could be awful. It could be great. We're going to talk about the seasons. I'm going to actually try and talk about them and debunk a couple of the bad ideas out there, and maybe talk about some of the right ideas out there. The number one answer we get in astronomy with seasons and why we have them is that the Earth is actually closer to the sun. And that's why we have seasons. And then it gets further away, and then it gets closer, and it gets further away. If that were the case, seasons on the Earth would all change at the same time, right? The northern and southern hemisphere have different seasons. Meaning, if it's summer in the northern hemisphere, it's winter in the southern hemisphere, right? So if this were to happen, we'd all be going into summer, we'd all be going to winter. So that can't be it. The other question, or the other answer that we get, is that when the tilt of the Earth makes one part, the northern hemisphere, closer and the southern hemisphere further away, that sounds actually pretty decent, right? It's about 2,000 miles closer out of 93 million miles. It's not even a percentage closer. The sun doesn't even realize it. That makes no difference, is what I'm trying to say. So the closeness of the sun has nothing to do with it at all. So if it's not all about how close we are together, what's it all about? What causes seasons? The seasons are caused by the tip of the Earth. We're tipped 23.5 degrees. I imagine a few of you could tell me that we're tipped 23.5 degrees. Well, what are we tipped according to? That's where everyone stumbles. No one knows what we're tipped according to, right? An angle has to be measured off of something. So what are we measured off of? It's measured off of a term we call the ecliptic. And I'm going to show you in a diagram what that is and how we define it. I'm also going to talk about that tip. I'm going to talk about a thing called insolation. And finally, I'm going to get into the idea that because of this tip, the northern hemisphere in the summer gets longer periods of daylight. We get like 14 hours of daylight. And in the winter, in the northern hemisphere, we get like 10 hours. And that's going to play into this whole seasons idea. So let's talk about that. All right, here's the sun. Now, let's turn on the equator of the sun. There we go. Now, if you were to project a plane out from the equator, that is what astronomers define as the ecliptic. So that's what I've done. Now, let's actually go take a look at the Earth. I've put the poles and the equator on the Earth. Now, if the Earth were upright, that's what it would look like. But it's tipped. It's tipped 23.5 degrees according to the ecliptic. And now you can see it. So that is what the Earth actually looks like. So here we are at one of the labs where I work, and here is a demonstration on insolation. We have an overhead projector, we have an Earth globe. Right here, on that overhead projector, I'm going to be projecting a square. You can see it's a nice happy square, it's not a rectangle, it's a square. I'm going to put that here, and this is going to represent the sun. So now the sun is shining on the Earth, and you can see that square is being projected on the Earth, and that's going to represent insolation, incoming solar radiation, not insolation, insolation, S-O-L. Now, when the sunlight comes in, it's actually coming in what we call collimated. It's coming in parallel. It's not coming in at angles. By the time it gets to the Earth, it's coming in pretty straight. So when it comes in this bundle. Look, and when it's coming in on a square near the equator, it's being projected pretty tight and pretty intense. But watch, when you take that and project it higher up, because the Earth's a sphere, look what happens. That same square is now, it's being spread out over twice the area. It's covering twice as much. So that means that it's going to be a lot less intense. Does that make sense? So, really intense, not as intense. Now, to just prove this to you and reiterate this even more, I'm going to change this out for an overhead with lots of squares. So I'm going to put that on there. And now you really get the idea here. Look, and you see in the middle of the Earth, it still looks pretty squared. Right? It looks like there's still lots of squares, but as you get out towards the edges, like over here, they start to really get pulled out, and you're getting a lot less intensity at the top of the Earth. You're getting a lot less intensity. The rectangles start to spread out, and that is going to cause a difference in temperature, a difference in intensity. So there you go, insolation in a nutshell. So I've made a few different diagrams to show how we get more or less daylight depending on the Earth's relationship to the sun. Here you see the winter solstice. It's the shortest day of the year in the northern hemisphere, and for someone like me in Philadelphia, we get about 10 hours of daylight. Now I've added the vernal and autumnal equinoxes. It's the first day of fall and spring. You can actually see that the sun is much higher in the sky, and it actually will last for about 12 hours instead of 10. Finally, I've added the summer solstice. It's the longest day of the year in the northern hemisphere, and it has about 14 hours of daylight. So why does the tilt of the Earth cause installation and longer days? Well, here's why. Here's the tilt of the Earth, here's the northern hemisphere, here's the southern hemisphere. The northern hemisphere in the summer is tilted in towards the sun. So what's happening is you get the really direct rays. You're getting the square, not the rectangle. In the southern hemisphere, you're getting the rectangle. You're also getting like 13 to 14 hour long days up here, so you're getting longer, intense, more light. Down here, you're getting less. You're getting like 10 hours of daylight, and it's spread out over a bigger area. In the winter, when the sun goes around, or the Earth goes around the sun, here's the sun, and now look, the southern hemisphere is now in the direction the southern hemisphere is tilted in, and the northern hemisphere is tilted away, and thus it's the opposite effect. So that's all I got from you today. Seasons, yeah. Hopefully you guys know everything there is about seasons. That's just a basic guide for seasons. In case you're wondering what would happen if the Earth wasn't tilted, I've always asked this question. We'd probably have some pretty extreme weather. The equator would probably be hurricanes all the time. We'd have a tornado alley all the time. Tornadoes everywhere. It would be really cold at the poles. It would be out of control. If you guys like what I had to say and you want to listen to some more stuff, hopefully in about a month I'll do another one on some other crazy topic. If you want to tell me some topics to talk about, feel free. But feel free to subscribe or leave some comments. Thanks, guys.